is our first week of class, so nothing's due this week. Just letting everybody settle in. Next week on Friday, your quiz 1 is due. I just passed out the some printouts of it. It's also in Moodle. It's a non-collaborative assignment. You should do that on your own. It says at the top. So that's due next week, and then the week after Project 1 is due. And the week after that, we review and then take the test. So already feels like it's moving along fast. All right, so today we're going to start Chapter 6. So this is officially new material. All right, so we're going to start off with an easy question. What's the derivative of x squared plus 3x plus 2? 2x plus 3. Great. All right, so we could say this another way, sort of going backwards. We could say an antiderivative of 2x plus 3 is x squared plus 3x plus 2. Can you think of a different antiderivative for 2x plus 3? X squared plus 3x plus anything. Because when you take the derivative, that constant's derivative will always be 0. So 2x plus 3 has a whole family of functions that are its antiderivative. So the general antiderivative of 2x plus 3 is a whole family of functions, x squared plus 3x plus c, where c is an arbitrary constant. All right, so we want to find the general antiderivative of each of these. So if f prime of x is cosine x, the general antiderivative f of x is what? Sine x. Yes, we're trying to think of a function whose derivative is cosine. So that would be sine of x. And because we're trying to write the general antiderivative, we have to write a plus c, plus an arbitrary constant. So it's a very subtle difference in language. Find an antiderivative. You can write any c you want, and usually the c we choose is 0 because it's the easiest. But when you want the general antiderivative, you got to use the plus c. All right, general antiderivative of f prime of x is 4x cubed plus 1 over 1 plus x squared. X to the 4th. X to the 4th plus what? Yeah, it's arctan. Yeah, the function whose derivative is 1 over 1 plus x squared is arctan x. And then we need a plus c. All right, so suppose you have the velocity and position functions for some particle at time t, then blank is an antiderivative of blank. Yep, good. Position is the antiderivative of velocity because velocity is the derivative of position. So if I give you a velocity function, like say v of t equals 2t plus 3, can you tell me where the particle is at any moment? Yeah, because v of t would be the speed, right? So you know how fast it's moving, and the antiderivative s of t, position, is position, but when you take an antiderivative, it's got this arbitrary constant. So you have to know which antiderivative in order to actually fill this in, to know the position. So we need, you can think of it two ways, an initial position to find the arbitrary constant. The plus c. All right, so this is sort of the heart of Calc 1 written in 4 lines. So this is to remind ourselves about the relationships between a function and its first and its second derivatives. So f prime positive means f is increasing. And if f is increasing, you know f prime is positive. Okay, those two things are equivalent. F prime negative, f decreasing, equivalent. All right, so then when we go to the second derivative, because f double prime is the derivative of f prime, we have the same relationship between f double prime and f prime as we do between f prime and f. So if f double prime is positive, that tells me that f prime is increasing. It's just this exact line written right here, but instead of f prime and f, it's f double prime and f prime. But then if you know that f double prime is positive, you know that f prime is increasing, you also know that f is concave up. And if f double prime is negative, that means f prime is decreasing and f is concave down. So we have all these relationships that we're going to try to use in a different way than we did in Calc 1. We're going to try to work backwards from f prime to f. So we're applying what we already know, but in a different way. And the idea is we want to try to sketch the antiderivative of this function. Okay, so this is the graph of f prime. We want to sketch its antiderivative, f. So I'm going to mark up the top one with whatever I know about f. So if this is f prime, if I go back to this, let's see, if f prime is positive, that tells me something about f. F prime negative tells me something about f. And f prime, where it's increasing and decreasing, also tells me something about f. So I have to look for places where f prime is positive and negative, and places where f prime is increasing and decreasing. Oops. All right, so if I look at just this region, that interval of x, is f prime positive or negative? Positive, because this is a graph of f prime. It's above the x-axis, so f prime is positive. And is f prime increasing or decreasing? Increasing, because it's going up. There isn't much analysis we have to do. Like, you're not picturing tangent lines because this is the graph of f prime already. So here we have f prime is increasing. All right, so what does that tell me about f? F prime is positive. What does that tell me about f? F is increasing. Yep. And f prime increasing, what does that tell me about f? That it's concave up. I'm starting to draw on my where I want to draw the actual graph, so I'll do it up here. F is increasing, F concave up on that interval. All right, so then let's look at the next sort of important interval. From here to here, F prime is positive because it's all above the x-axis, but F prime is decreasing. Right. So F prime positive, what does that tell me about F? Increasing. So on this interval, I've got F is increasing, and F prime decreasing tells me that F is concave down. All right, then we go to here. On this whole interval, F prime is negative, it's all below the x-axis, and F prime is decreasing. Okay, so that tells me that F, if F prime is negative, F is decreasing. F prime decreasing, that tells me that F is concave down. Right, and then this last stretch here, I've got F prime is negative, all below the x-axis, and F prime is increasing, right, heading back up towards 0, so it's increasing. So that tells me that F is decreasing, right, the negative derivative says F is decreasing, If f prime is increasing, that tells me that f is concave. All right, so now I'm going to use these descriptions to draw the graph. Okay, what I don't know is a starting point, right? Because if I'm drawing an antiderivative, it's going to have an arbitrary constant. So you just have to kind of pick a starting point and then follow these directions. So I'm going to pick my starting point right here. Totally arbitrary. Just have to pick a value for f of 0. Okay, so now I'm supposed to be increasing concave up until here. Increasing concave up, so something like that. And then from here to here, supposed to be increasing but concave down. So I continue increasing, but I just change concavity. All right, and then in my next interval, from here to here, f has to decrease but be concave down. So something like that. And then from here to here, it's supposed to decrease but be concave up. So it continues going down, but just changes concavity. So like that. Now I could have put my starting point anywhere. Any graph that is a vertical shift of this one would also be an antiderivative. So I could have started here and followed my directions exactly the same. And gotten a different antiderivative. All right, why don't you take a minute and try to sketch an antiderivative of this function. All right, so this is our graph of f prime, right? So I need to know about f prime's sign and about where f prime is increasing and decreasing. That gives me information about f. So f prime's sign, everywhere that I have shown, f prime is always positive or negative? Positive. So if f prime is positive, that means f should be increasing. So when I draw my graph of f down here, it should always be increasing. Left to right, always going up. All right, so then I have to think about where f prime is decreasing and increasing, because that tells me the concavity of f. So at this point right here, I have a switch. F prime changes from decreasing to increasing. F prime decreasing means that f is concave down. Right? And f prime increasing over here means that f is concave up. So I have to draw a picture of f that is always increasing and is concave down, then concave up. And you pick any starting point, right? You can start at 0, 0. That's sort of a common place to start. I'm going to start a little bit lower just because I know it's always going to be increasing, so I won't run out of room. So I'll start down here, and I have to increase until this x value, concave down, then continue to increase, but be concave up. Something like that. That kind of looks like a line. There we go. That make sense? Okay. All right, I want to talk about the challenge because I was looking at it this morning and it's an interesting problem. Take some time to wrap your brain around. So we have a graph now of f double prime. So we could analyze f prime the same way we just did the previous two examples. Think about where f prime is positive and negative, increasing and decreasing. Sorry, f double prime. Think about where it's positive and negative, increasing and decreasing, and you can get some information about f prime. So some of these, the last two, E and F, are pretty easy because this is a graph of f double prime. So where is f double prime the greatest? At what x value? x1, it's just the biggest y value. Okay. And where is f double prime the least? x5. All right, so now I have to think about f prime, the antiderivative of f double prime. So I would say, all right, well, f double prime from x1 to x3 is positive, which means that f prime is what? Increasing. F double prime is positive, that means its antiderivative f prime is increasing. And then from x3 to x5, f double prime is negative, which means that f prime is decreasing. Yeah. So f prime is increasing from x1 to x3 and then decreasing x3 to x5. So where is f prime the greatest? x3, because it goes from increasing to decreasing, right? So that has to be the biggest point, x3. All right, and then where would it be the least? F prime, where would it be the least? x1 or x5? They seem, I think they'd be the same. And then you have to think about f. Where would f be the greatest and where would f be the least? And here's where this information has to be used. F of 0 is 0. And f prime of 0 is 0. So I got to figure out where is f the greatest and where is f the least. So maybe if I sketch f prime, that might help. I know a lot about it now. I know f prime of 0 is 0, and that's a max. Yeah, so these have to kind of go, well, I should line it up with x is down. And then this goes down till x4. Then what happens? Yeah, this is just a line because this looks like if the blue is the derivative of the purple, then this looks like the derivative is approaching a constant. And what kind of function has a constant derivative? A line, right? So this looks like it's gonna like be a line like that. And then this too. All right, so now that we have f prime sketched, can we try to work towards f? Okay, I know f of 0 is 0. That was given. And now I'm looking at f prime, and I say, okay, well, from x1 to x3, f prime is negative, which means that f is increasing. F prime is increasing, which means that f is concave up. Yeah, concave up. F prime increasing, f is concave up. So f prime's negative, so we're decreasing, concave up. So I have to be decreasing and concave up here for f. And then f prime is still negative, which means that f is going to continue to decrease. But now f prime is decreasing, which means f is going to be concave down. So something like this. So where is f the greatest? x1. And where is it the least? x5. All right, so just another reminder, when f prime is increasing, f is concave up. And if f prime is decreasing, f is concave down. Okay. All right, the fundamental theorem of calculus can let us actually calculate values of an antiderivative from the original graph if we're able to find the integral. And right now we find integrals just by looking at areas. That's sort of the only method we have of finding an exact integral. All right, so here's a graph of f prime from -4 to 4. And I know that f of -4 is 0. That's the only value of f that I know. But I want to fill in this table of values for f. And I can use the fundamental theorem. So if I just want to figure out the value f of -3, I know that the fundamental theorem says that if I take the integral from -4 to -3 of f prime, right, the integral of a rate of change equals total change. So I would do this by doing f of -3 minus f of -4. And then plug in the stuff you know. I know f of -4, they told me, was 0. F of -3 is the thing I'm trying to find out to fill in this table. Do I know the, or can I figure out the integral from -4 to -3? Yeah, it's the area under the curve from -4 to -3. So it's the area of this triangle, which has base 1 and height 2. 1/2 base times height, so that's a 1. And it's negative because it's below the x-axis. So f of -3 is -1. Then you can do the fundamental theorem again between -3 and -2, and -2 to -1, and -1 to 0. And you can keep using the fundamental theorem to fill in all the values of this table. So let's figure out f of -2. So I can take the integral from -3 to -2 of f prime of x dx, and that should equal f of -2 minus f of -3. And the integral from -3 to -2, that's the area of this triangle, which is +1. Same as the previous one, but above the x-axis. So 1 equals f of -2 minus f of -3, which is -1. So f of -2 is 0. All right, finish up filling in the table. Use the fundamental theorem to calculate the rest of these values. So f of -1 is 1.5. And then what'd you guys get for f of 0? 2. All right, and then for f of 2, I'll do this one out because suddenly we're trying to find the area of a different kind of shape. So if I want to find f of 2, then I should integrate from 0 to 2 and use the fundamental theorem. Oops. So I'll do it down here. Integral from 0 to 2 of f prime of x dx. That's f of 2 minus f of 0. All right, so I need the area under f prime from 0 to 2. So that's this area here, which is 1/4 of a circle of radius 2. So the area of a circle is pi r squared. So the area of a whole circle of radius 2 would be 4 pi, but it's just 1/4 of a circle, so its area is pi. So I come down here and I say, okay, pi is equal to f of 2, which is what I don't know, minus f of 0, which is 2. So f of 2 is pi plus 2. And then you do a similar thing for finding f of 4, and what did you get for that? 2 pi plus 2. All right, let's do it out. Okay, so let's see. I need the integral from 2 to 4, which is going to be pi. F of 4 minus f of 2. This is pi. F of 4, I don't know. F of 2 is pi plus 2. Right? So then add pi plus 2 to both sides, and I get 2 pi plus 2. Yeah. Yeah, 2 pi plus 2. So it's probably just a distributing or not distributing this negative sign if you got a minus. Great. All right, so if you don't have a handy dandy graph that's really easy to find the areas under because it's all lines and circles, you can do this exact same approach, use the fundamental theorem to write an equation and solve for the value you want, and just use your calculator to get the integral part. So if I know that f prime of t is ln t, do we have a function off the top of our heads whose derivative is ln? Any formulas that you can remember? No, the derivative of ln is 1 over x. Yeah, so but there is no function that we've studied whose derivative is ln of x. So I can't just come up with a function, right? But I can figure out values of this function. I can figure out what f of 2 is, the antiderivative of ln. If I know f of 1 is 4, I can figure these other things out using the fundamental theorem. So the integral from, let's say, 1 to 2 of f prime, which is ln, should equal the antiderivative f of 2 minus f of 1. So the integral from 1 to 2 of ln t dt, that just means the area under the ln curve from 1 to 2, and our calculator can do that for us. Okay, so ln x, and I'm going to graph this. Go 0 to 3. And okay, I guess I didn't need to go to 6. Let's go to all right, there we go. So what I need is this integral from 1 to 2. I need the area under this curve from 1 to 2 in order to plug into my equation of using the fundamental theorem. So if I do calc option 7, put in my lower limit as 1 and my upper limit as 2, it shades the area and tells me how much it is. So this is the exact same problem we just did before. This is the graph of f prime. I just can't calculate those areas by hand because it's not just lines and circles. So my calculator tell me that this is 0.386. And f of 1 I know is 4. So f of 2 is 3.86. Sorry, 4.864. 4.386. Yeah. All right, you guys find f of 3 and f of 0.5. So There's a challenge question if you want to work on it. This one's actually not that crazy, so you can play around with that question for a little bit, and then you can move on to Sketchy Sketches. So these are antiderivatives. I'm sorry, these are derivatives. Graph the antiderivative of these guys, and feel free to round out, mentally smooth out the corners. That helps you draw it. And there are some answers to these, but keep in mind that any vertical shift of these is fine because there are many antiderivatives.